Hello everyone. In this lecture we are going to discuss about minor losses, and we have already discussed them in brief in our previous lectures, but this lecture is completely dedicated to only that topic. Now, anything that can be called a minor loss is just all those losses which are not the friction loss along the length of the pipe. That means loss due to entry, exit, contraction, expansion, then pipe fittings, valves and branches and all those things. Now, to find out the minor losses, we'll use these kind of formulas where, for example, you can see loss at entry is given by k into v square by 2g. That means it's expressed as some function of the velocity head where it is multiplied by some coefficient k, and the value of this coefficient k will depend on different types of losses. Out of all these formulas, only two different formulas are loss at sudden expansion or enlargement of the pipe, and loss at exit. They can also be converted to the same formula, same format, which is k into v square by 2g, but as we have already learned in case of loss at exit, that k would be always 1, because whatever velocity head is remaining at the end of the pipe, whether it is releasing the water into the atmosphere or if it is releasing into some kind of a tank, that velocity head can never be restored. It is always lost to the surroundings, and therefore there is no point in remembering the value of or making a list of values, because that value of k is always equal to 1. In case of sudden expansion as well, we have a separate formula. We'll discuss that later, and since this formula is, you can derive it, it's well established, therefore there is no point in converting it to these other forms. So now let's get to the first kind of minor loss, which is loss at entry, and that is when water enters a pipeline. It may be from a reservoir or tank. So when it enters, for a small length, the flow lines actually converge. That means they try to get closer to each other, and that causes this kind of a conversion very near the mouth of the pipe, the entry of the pipe, and near the pipe boundaries a low pressure region is created, because of which the flow creates some kind of turbulence, and because of this turbulence some head is lost, and that head loss is given by this formula k into v square by 2g, where v is velocity inside this pipe. Now this k depends on the shape of the inlet. That means if it's a very sharp inlet like this, then we'll have those turbulences here, and the value of k in this case, that is, which is a very sharp inlet, in this case k will be approximately 0.5 or something around this value. But we can reduce this head loss by making a smooth entry or smooth transition. That is, if we make the transition like this, what we are doing here is that we already know that the flow lines will converge, therefore we make the pipe boundaries or the entry to the pipe coincide almost with the streamlines or the flow lines, so that after conversion, whatever reduced cross-sectional area the flow acquires, it becomes equal to the actual area of the pipe. In the previous case, that is in this case, after conversion the area of flow becomes slightly smaller, than the actual area of the pipe. And therefore, to fill this empty space, this water came back and created all these turbulences. But in this case, that is not going to happen, because after conversion, after convergence, the flow cross section will be almost equal to the pipe cross section itself, and therefore the K value will be greatly reduced. It can even reach 0.02, 0.04, these kind of values, which is a much better improvement than this kind of a setup. You can, if you want, you can increase this value by making the inlet a little bit difficult. That means flow will be entering like this. So in that case, it can go up to 0.7, 0.8, etc. Now this is about head loss at entry. Then comes head loss at exit, and we've already discussed this is simply v square by 2g. There is no k involved here. K is always 1, and the shape of the outlet does not actually matter. So if this is the outlet, which is suppose releasing into some kind of a tank or reservoir, it doesn't matter what is the shape of this outlet. This amount of head will be always lost, whatever is the velocity head inside the pipe. Now we can interpret it in a different way. If we make a smooth exit, like this, then what will happen actually? In that case, you'll see that whatever is the velocity at this cross section, velocity will decrease, because cross sectional area has increased, and therefore velocity will decrease. At this cross section, velocity will further decrease, and therefore this v term will decrease, and v square by 2g therefore will decrease, and that in turn will show us that the head loss is decreasing. Now at a sections slightly around here, just upstream of the main reservoir, in that case the area will be very large, and therefore the v will be very small, and then we can say that there is almost negligible head loss. But actually that is not the right way to think about it, although technically that's true, but we are not going to find out velocities at all these different cross sections very near the exit point. We are only concerned about velocity at the main pipeline, and therefore it's better not to think of it like this, and whatever velocity is there and the corresponding velocity head v square by 2g will be lost. Now loss at sudden contraction it's similar to head loss at entry. If we consider a large pipe and suddenly it became a small pipe, the diameter decreased. So in that case, similar to entry into a reservoir, all these flow lines will converge, and a similar situation will be created just like entry from a reservoir. Now the situation will not be as bad, because many of the flow lines were already flowing in this direction. So therefore this scale value will be slightly smaller than whatever it was for the loss at entry from a reservoir, but still it will be there. If you if you consider a transition where it's a very large pipe which is changing into a very small pipe, so in that case velocity in this pipe is very small compared to the velocity that would be in this smaller pipe, and therefore its velocity can be almost ignored, and it will be a very similar case to that of loss at entry from a reservoir. But anyway, the K value will depend on the shape of this transition. Then if we look at loss at sudden expansion or enlargement, that means if a pipe increases its diameter, then again some turbulence will take place at this point, and that head loss is given by this. Now this formula, if you look at it, if we consider a very large pipe, then it will be similar to loss at exit, which is a pipe releasing the discharge into a large reservoir. So that means the flow inside this very large pipe will be almost static compared to the velocity in the smaller pipe, and therefore this equation becomes very close to the head loss equation of exit at the exit of a pipe, because as this area increases, the V2 velocity decreases, and for a very large pipe compared to a smaller pipe which is enlarged, in that case this V2 will be almost negligible compared to V1, and this whole equation will be only be similar to this equation. Now head loss at gradual enlargement and contraction, it's if instead of this kind of enlargement or contraction, if we can make them very gradual like this or this, then the value of K will be decreased drastically actually, and depending on how smooth these transitions are, that is compared to this kind of a transition, if the transition is made like this, then the K value will be further smaller, a very small negligible value. So this is how we can reduce this kind of head loss if we want. Now let's come to loss at bends. Many times we have to connect different pipes which will be flowing in different directions, and therefore it involves bending them like this at different angles. And if we look at this graph, we can see that the x-axis is centerline radius of the bend divided by internal diameter of the pipe, and y-axis gives you the value of this K. In this chart it is written as KB, that is K for bend. Now it depends on the angle of bend, the curvature of the bend, and also a connection type. This graph gives you the first two variables. Now how do they affect us? The angle of the bend is just how much the water is or the pipe is deflected. In this case the angle is very small, that means it is only this much. Remember, the angle is measured compared to the original direction of flow. This was the original direction of flow and this is the new direction of flow, therefore between them this angle will be measured, and we can increase this angle by 90 degree to 90 degree like this, and even greater than 90 degree, means this was the original direction and this is the new direction. That means the change in angle is this much, suppose 120 degree or something, which is greater than 90 degree. We can also have 180 degree bends like this. So if the angle of the bend increases, then the KB value will also increase. And therefore, to show different values of these angles, there are different curves. That is, this topmost curve is for 180-degree bend, which is this bend, and for this the value of KB will be highest. And for a 10-degree bend, which is the lowest curve, the value of KB is in a very small range. Now, it also depends on this next criteria, which is the x-axis, which is central line radius of the bend by internal diameter of the bend. And it means that if we have a bend like this, in that case the central line radius of the bend means if this is the central line of the pipe, then what is this radius at the bend? So this radius is in this case very small, and compared to, if we compare it with the diameter of the pipe, that is this diameter, then we will get a smaller ratio. But if we make a bend like this, which is obviously a smoother transition or smoother bend, in that case the central line radius of the bend will be this much, and this radius by this diameter is a larger ratio than this radius by this diameter. And as we can see, for all the different angles, whether it is 10-degree bend or 90-degree bend or 180-degree bend, for all of them, as this ratio increases, this R by D ratio, the KB value decreases. That means for this second example, the value of KB will be smaller than KB for this example. And that's from our common sense also, we can simply guess that, because it's a sharper bend and this is a smoother bend. Now connection type is also important, because if we can simply bend the pipe itself, then it will be much more efficient rather than using some other kind of connection that you must have seen in household plumbing. These kind of connections are available, elbow joints they are called, and they are connected to two different pipes. So in this case there will be some, because the inside of the this joint is not completely flush with the inside of the pipe, and therefore some more loss will be happening inside, some more turbulence will be caused, and therefore the value of K will increase. Now let's come to loss at pipe fittings. So pipe fittings may be of different types. One may be joints. Joints are used if we want to lay a very long pipeline. The commercially available pipes will be only of a few meters, and we'll have to join all these pipes at different intervals, and while joining them we'll have to use different connectors, and all these connectors, depending on how well they fit, will have some kind of this K value, and that K value will be multiplied with V square by 2G. Similarly, pressure gauges, if we have a pipe like this, if you want to measure the pressure here, then we will have to fit some kind of a pressure gauge like this with some kind of a dial, and this will be inserting a small, not exactly inserting, this will be connected with a small tube, very small tube, which will be connected to the flow inside, and it sometimes may cause a very small negligible amount of head loss. If if it is properly installed, then the head loss will be minimum, very negligible. Flow measuring equipments may also cause some kind of head loss. For example, in this pipe, if we want to use the flow rate, then we may use a venturimeter, which we have studied in the previous semester. And this venturimeter, since it's one kind of a disturbance, it will cause some amount of head loss, and that is again classified under this minor head loss. Flow restricting fittings, that means sometimes we may want to reduce the flow rate in some cases, and those kind of fittings will also cause some kind of head loss. Filters or traps, they are also provided to stop some other solid material to pass along with the flow. They are also used in case of sewer lines or storm drains, which carry the wastewater or which carry the rainwater from one place to another. These are very large underground pipes, and in those pipes, many at different places will use this kind of traps, which will trap the debris or garbage and all those kind of things, and from time to time they will be removed and cleaned. So they also cause some amount of head loss, as water has to pass through these kind of smaller openings instead of a unobstructed cross section. So this is about traps and filters. Now finally, let's come to valves. So these valves are used for flow control, either to stop flow or open, and to have any control in between. Now, similar to all the other types of head losses, here also the formula is same, K into V square by 2G, but the K value in case of head loss, valves, is a variable value and it's not constant. And that's because if it is completely open, if the valve is completely open, then the value of K is very small, which will cause very small amount of head loss. However, if we keep on closing the valve gradually, then the value of K will increase, and therefore the head loss will increase, and therefore the flow will be obstructed. And if it is completely opened, completely closed, then this K value can even go to, it can be considered infinity. That means it has completely stopped the flow. Now these valves will come in different shapes and sizes and types. There are different types such as ball valves, butterfly valves, check valves, and all those types of valves. Here a ball valve will be something like this, a ball with an opening like this. This opening will be aligned with the pipeline through which flow will be passing to the other side. Now this ball can be rotated. If it is rotated, then instead of facing this way, this opening will face this way, and in that case the pipe will the pipe flow will hit this solid wall and the pipe flow will be stopped. And this rotation can be done by providing a handle like this handle, and it can be closed or opened. It can be turned by 90 degrees. Similarly, there are different kinds of valves like gate valves, which is kind of like this, where if this is the pipe cross section, the gate will be outside, but as you keep rotating this handle or knob, this gate will be lowered and the cross section of the pipe will be gradually closed. So these are the different types of valves. Now some valves are used for quick opening and closing. For example, this valve, where you can simply turn it 90 degrees to close the valve, and again turn 90 degrees to the other side to completely open it. And some other valves are used for fine controlling. For example, this valve, where you can open or close it with a much better precision. Now the final part is loss at pipe branching. A pipe branch is where flow from one pipe can be transferred to another pipe. So they will look something like this. So this kind of a branch is called T branch, and this is called a Y branch. They're called so because they look like those English letters T and Y. There can be a cross branch as well, which will be something like this. So all these branches will also cause some kind of head loss, and again the head loss is given by similar formula. The head loss is equal to K into V square by 2G. But you have to look at the formula and remember that this V is generally for the line along which we are finding out the head loss. That means if we want to find out head loss in this pipe, this branch, then we'll have to take this velocity and use the K value for this pipe, this section. So there are two kinds of these coefficients or K. It can be for line flow or it can be for branch flow. Line flow means if this is the T branch, suppose, then for this direction of flow it is called line, and this direction is called a branch. And for this the K value will be different, approximately suppose 0.8 or 0.9, and for the line flow generally the value of K is slightly less, around 0.3, 0.2 and so on. Again, these either these kind of branches or bends and all those things, they can be connected in different ways. So they can be flanged connections or threaded connections. So a flanged connection is like this, where we use a flanged end of the pipe and also a flanged end of the connector. That means if this is the pipe, at its end it will be flanged like this. If we want to draw it better, then it will be something like this. And on top of this we'll use the other connector, which is the, suppose, the T joint, and we'll bolt them together on both sides so that they're tightly connected, and in between there may be some kind of sealing compound or sealing layer like rubber or silicone or those kind of materials. And the advantage of this kind of connection is that you have a very smooth surface of flow. If you draw the cross section, or sorry, the longitudinal section, it will be looking like this. And this portion is very smooth, there is almost no obstruction. However, the other kind of connection is called the threaded connection, which will be like this. So the inside of both these connections will look like this, and the problem with this kind of connection is that if we have a pipe cross section like this. Suppose this part is the thickness of the pipe, and the outside of the pipe will be provided with some kind of thread, and the inside of the connector will also be provided the similar kind of thread, and it will be joining it with another pipe like this. And because of this kind of a connection, there is this obstacle, because the cross section of this pipe and the inside of this connector are not same, and at these junctions there will be some additional head loss, additional turbulence, and therefore head loss, and therefore in threaded connections the value of K is generally more than that in flanged connections. However, in most of the household plumbing problems we use this kind of connectors because they are very cheap, and to have a flanged connection you'll also have to provide the flanged end of the pipe. But if we keep cutting the pipe to different required lengths, then we cannot have the flanged end of the pipe, although the flanged end of the connectors can be bought, but the pipes cannot be flanged very easily, and they have to be prepared in the factory. So this is all about our minor head losses that we had to discuss. Now in our next lecture we'll discuss about flow of water or flow in series of pipes or a parallel set of pipes. So this is all for this lecture. Thank you.